Hello guys, in this video we're going to see some examples of reflexive spaces and the relationship between reflexivity and separability, and we're going to have a look at some theorems for reflexivity, and that's pretty much it. Without further ado, let's get started. So example number 1 says that every finite dimensional space X is reflexive. Now let n be equal to the dimension of X. Let the dimension of X be equal to n. So that Ix is an n-dimensional subspace of X star star. Why so? Because Ix is an isometry. And we know that in the case of isometry, in the finite dimensional setting, the dimension of X is equals to the dimension of I of X. The next thing is, we know that dual space of a finite dimensional space has its same dimension as the space itself. So the dimension of X is n, then the dimension of X star is n, and so the dimension of X star star is also equals to n. But now we see that I of X is an n-dimensional subspace of an n-dimensional space. So I of X is a subspace of X star star, and both of them has the same dimension n, so I of X is equals to X star star, and therefore my space X is a reflexive space. So in this example, we're going to prove that my space LP is reflexive. Now if you remember, if I want to prove that a space is reflexive, I need to prove that this mapping I given by Ix of t is equals to t of X is surjective. Once I prove the surjectivity of this mapping, I can say that my space X is reflexive, okay, where X is an element in LP. So let's see the construction as we go forward. So we have an element Y in my space LQ, you can see here, and my space LP star, there is an element T. You know that LQ is isometrically isomorphic to LP star. So if I do this operation, if I apply T, which is an LP star, to an element in X, which is an LP, I would get a scalar in the field. It might be complex, it might be real. So again, I did this operation here. So what I did was I applied T, which is an element of LP star, to my X, and I find out that it turns out to be this. And similarly, if X is in LP and S is in LQ star, so what we are doing is that when I apply this operator S to an element in Y, it gives me a real number or a complex number depending upon my scalar field. So S applied to Y gives me this. Now if you look carefully, then you can see that a T is an element in LP star, which is identified with Y. So if you see, this is the identification between T and Y, because we have seen in the previous videos that LP star is isometrically isomorphic to LQ, so they can be identified with each other, which means they are the same but not the same. Again, in the similar way, X is identified with S. So again, since LP is isometrically isomorphic to LQ star, so elements here can be identified with each other. And now the interesting thing is, I have this identity. So I of X of t is equals to t of X is equals to this summation. Now this identity is fixed. It is like a predefined function. You can think of it this way. So this isometry, now look at this isometry carefully and you'll see that this Y can be identified with T. So I of X can be identified with S, but S was identified with X already. So I of X can be identified with X. So eventually what happens is I of X gets identified with X, and thus I gets identified with the identity mapping. And once we know that, once we do that, then we can say that like all identity mappings, I is surjective, and therefore I can say that my space LP is a reflexive space.
Point number 4 says that the space L1 is not reflexive. It is separable, but its dual space, which is isometrically isomorphic to L infinity, is not. So the dual space of L1 is L1 star. And it's isometrically isomorphic to L infinity. Now we know that L1 star and L infinity are not separable, and therefore my space L1 is not reflexive. You can see it from the formula or from the remark. A reflexive space is separable if and only if its dual space is separable. So in the last section, I would like to discuss why my space C0 is not reflexive. So just a reminder, C0 is the set of all sequences that converge to 0. Now the way I progress in this proof is also very similar in the way that I did in the last proof. So what I did is I take that same to here. I take my space, I take a point y in L1 and I identify y with t. So just like the previous example, so I apply my operator t to the elements of my set x. So as in this case, you can see that this makes perfect sense because t belongs to C0 star and x belongs to C0. So I get this quantity here. Similarly, I apply my operator s to elements in y. So s is L1 star, which is identified with L infinity, and I apply this operator s to elements in my to elements in my space L1. So I have a y, a sequence in L1, and I apply s to y, and I get this. Now I have I of x, which is my linear isometry, so its definition is given like this. And thus, if I just look at this part, just this part here and this part here, so I've identified y with t as before. That is C0 star with L1. I've already identified. I know that C0 star is isometrically isomorphic to L1. And thus I have identified I of x, which is C0 star star, because it's applied to an element which lies in C0 star. So I of x should be C0 star star. And I have identified this with L infinity because my S is in L1 star, which is isometrically isomorphic to L infinity. So I of x is identified with L infinity. And now when I see my isometry, now when I see this I, then this I goes from C0, which was my x, to some element in L infinity. And I know that this mapping from C0 to L infinity is not surjective. So thus I can say that my space C0 is not reflexive. Again, the essential idea is my linear isometry I of x should be surjective. And in the example above, the way I showed this surjectivity was I identified this I with the identity mapping. How did I do that? I did that because I identified in the previous example I of x with s, which was identified with x. So I of x was identified with x, and since I of x lies in LP star star and it is identified with x, so I can be identified with the identity mapping. This was the case before, and in this case, if I apply just the same protocol, I have this I is not from LP to LP, but is rather from C0 to L infinity, and thus this I is not surjective, and therefore my space C0 is not reflexive.